Hey people, this is the next installment. All right, in this section, we're going to look at bonding. This is really a 30,000 foot view of molecular bonding. And again, as I said in the last installment, I'm sure many of you have discussed some of these things in the general chemistry course that you took sometime in your past. So bonding comes in very many flavors, and so we'll talk about those. I want you to appreciate that bonding in molecules is governed almost exclusively by the electromagnetic force. Actually, in particular, electrostatic forces. So that puts us on a footing that we know a little bit about, right? So the energy, the total energy of bound molecules. And again, a molecule is the formation of two or more atoms, right? So this is the formation of two or more atoms through chemical bonding. So the total energy of bound molecules is less than the total energy of the separated atoms. That might seem like that's common sense, and it should be, because clearly if you want to drive the formation of molecules, then clearly the energy of the assemblage should be less than the total energy of the atoms alone. And this energy difference is the energy required to break the molecule into its constituent atoms. And again, what's governing most of these processes is the electrostatic force. Now, surprisingly, if we looked at if we looked at atoms at relatively large distances, and relatively is the key word, at relatively large distances, there's going to be an attractive force. And that's a little non-intuitive, actually, and hopefully in this discussion you'll get a better feel for that. But especially if one were to take two neutral atoms, it's not necessarily clear that at relatively large distance there would be an attractive force between them. And conversely, as we bring these atoms very close together, that is at small separations, we have repulsive forces that are dominating. And that's a complicated state of affairs as well, because this is made up of not only electrostatic repulsion, which is the third grade science aspect to it, but it's also due to the Pauli exclusion principle, which again is not so evident. So let's look at some of the quantitative aspects of bonding. And so, in general, the potential energy as a function of distance between in this case, let's just look at two atoms, can be written generically as negative A over R to the N plus B over R to the M, where N and M are integers. Not clear that they should be integers, but that's how it works out to be. And so this is going to be responsible for the attractive piece. This is the attractive piece. And this will be the repulsive piece. And so typically, if one were to look at the energy as a function of separation between the two entities, we have an attractive piece. So this is the attractive piece, which is negative. The attractive component, and that's proportional to 1 over R to the N. And we have the repulsive piece. And so this is the repulsive component, and that's proportional to 1 over R to the M. And if we look at the sum of these, then what we get is something that looks like this. Okay, And so this now is the total. This is the total potential energy. Okay. And remember, this is 0. It didn't specify that. And the energy difference between 0 and at the bottom of the well is what's called the binding energy. The binding energy. So I'm going to stop right there actually, because the last 30-minute video took a couple of hours to upload. So I'm going to do these in smaller chunks. All right, so we'll pick it up from here. Talk to you soon.